but I'll tell everyone in the recording. You can go ahead and submit the attendance form, which is the second link down under Web Links 2. So you should fill that out even if you are watching in the recording. So you click it, and then you have to click the Browse To button. And if you scroll up to the top of the chat, I included some links to the slides I'm going to be using, and also links to the study guide. So I couldn't get my slides to actually show up here, so I'm just going to go ahead and share my screen. We'll just I need to zoom out, I guess. So we'll just look at the slides on my screen like this. Zoom out one more. Okay, perfect. Okay, so this is what I was saying before. Fill out the attendance form, and I gave you guys the links. Okay, so how do I do this? I want to do page by page. That'll let me. Okay. So here, I'm just going to start with some. First of all, at any point, just interrupt me, type in the chat if you have any questions about anything. So we're going to begin talking about just kind of going through this Exam 3 review. Exam 3 covers modules 5 and 6, which is probability. And I wanted to start with just a couple of tips which you can use for this exam and also for other exams. The first thing is to watch your decimals. You can end up with a mistake in the final answer if you round too soon. So I like to always say keep at least 3 or 4 more decimal places than the number requested. So meaning if the final answer, they say round to 3 decimal places, then when you're actually doing your work, don't round to 3 decimal places in the middle. Wait and keep 7 decimal places written down or 7 decimal places stored in your calculator until the very final step, and then only in the last step round down to 3 decimal places. Because if you round too soon, you can end up with the wrong answer. Secondly, read the directions carefully. Right? Does the question ask you for a fraction or a decimal? It should tell you how far to round. Right? These are the kind of things that, because it's in my math lab and it's automatically graded, you can get it marked wrong just for like these silly little errors. And then, is it asking you to count something, or is it asking you for a probability? So those are the kind of things just to really read carefully as to just what the question wants from you. And then here's just a kind of a very easy check. Remember, all probabilities are between 0 and 1. So if the problem asks you to find a probability, like what's the probability that blank, and you're doing your calculations and you come up with 1.4, you did something wrong. You have to go back and check your work. Right? That should be an automatic clue that there's something going on there, because probabilities are always, always, always between 0 and 1. Okay. So we'll start by talking about just a little bit of vocabulary, just to kind of orient ourselves. So the first thing is an outcome, which is the result of an experiment. Okay, so when we're doing with probabilities, like each individual outcome is called an outcome. So like, for example, if your experiment is rolling a die, 1, 2, 3, 4, 5, and 6 are each the individual outcomes, right? So 2 is a potential outcome, right? That's one possible result of your experiment. The sample space is the set of all possible outcomes. So in our example, the sample space is the set that has in it 1, 2, 3, 4, 5, 6. So one thing that we can say is like the size of the sample space is 6. There are 6 things in the sample space. Right? So if our experiment is, if there are 100 people and our experiment is choosing one of them out of a hat, right? Each of those people are an outcome. The sample space is the set that has all 100 people in it. An event is a collection of outcomes from a probability study. So it can be as small as, actually it can even be the event, the empty set, but it could be even a single outcome, or it could be the entire sample space, or anywhere in between. So we could talk about the event that you roll an even number. So that would be 2, 4, and 6. You could have the event that your number is less than 3. So then that would be 1 and 2. You could have the event that you roll a 5, right? So that would be a 5. You could have the event that the number you roll is 1, 2, 3, 4, 5, or 6, right? So the event could even be the whole sample space. So any collection of outcomes is called an event. Now here's something that is important to kind of know, because especially this textbook asks you a lot about things that are unusual. Whenever they ask you if something is unusual, the definition that they're using is less than a 5% chance of occurring, or less than 0.05. This isn't out of nowhere. That this kind of 5% cutoff you kind of see all over the place in kind of statistical theory. It's kind of, we don't really talk about p-values in this class, but like that's the kind of the standard p-value, like for any type of science, for like whether you can kind of publish a paper or not. That's kind of the threshold you need to be over. So there's justification. Well, there's whether it's justified or not, it's a common cutoff that's used for determining whether something is unusual or not. 5% chance of occurring. So it's not just our textbook that says that. Okay, so the next two definitions people tend to confuse. Mutually exclusive or disjoint is kind of the first definition, and independent is a different definition. And people confuse them, but they're actually really very different. For our purposes, mutually exclusive and disjoint are going to mean the same thing. Usually when we talk about mutually exclusive, we're talking about events, whereas just disjoint, we would be talking about sets. But from what we need, you can use them interchangeably. You can say that two events are mutually exclusive or two events are disjoint. So what does that mean? That it is impossible for both events to occur at the same time. So for example, if I pick a day on the calendar at random, right? I'm kind of moving my finger around and I randomly stick my finger on the calendar, right? And I look at what day of the week it is, right? So my sample space is, Sunday through Saturday, right? And one possible event is that it's Tuesday. So the event that it is Tuesday and the event that it is a weekend are mutually exclusive, or they're disjoint. It's impossible for the day that I choose to both be a Tuesday and also be a weekend, right? They cannot both happen at the same time. Okay, so that's what mutually exclusive or disjoint is. Now, independent is different. Independent says the fact that one event occurs does not impact the probability that the other event occurs. So, let's see, independent would be like if I'm picking a day at random, right, from, the whole calendar of the year, and instead of looking at, on the one hand, I'm going to look at what day of the week it is. On the other hand, I'm going to look up the weather for that day, and I'm going to say, did it rain on that day? So the events, it was a Tuesday, and it was a rainy day, are independent. Right? If I tell you, if I say the probability that it's raining on a given day is 30%, right? If I then give you this extra information, but just so you know, it was a Tuesday, okay, it's still 30% chance of raining on that day. Like, the fact that it's Tuesday doesn't impact the fact that it was raining. They're independent. So you can see how that's different than mutually exclusive, right? Because if instead of my two events being Tuesday and raining, my two events are Tuesday and weekend, then suddenly, right, if the probability of it being a weekend was 2 in 7, but now I give you this extra information, it was Tuesday, that absolutely changes the probability that it was a weekend, because the probability that it's a weekend just went from 2 in 7 all the way down to 0, right? If I tell you it's Tuesday, the probability of it being a weekend is now 0. It's impossible. So if two events are mutually exclusive, they're definitely not independent, because knowing about one definitely changes the probability of the other. And then I want to just quickly talk about permutations and combinations. In both permutations and combinations, as opposed to calculating the probability that something is going to happen, we're counting the number of ways for something to happen. Right, so we're going to say there's 15 possible ways for this to happen. And in both permutations and combinations, what we're going to do is we're going to start with a big pool of objects. Okay, how many things are going to be in our pool of objects? N of them. Okay, And we're going to figure out how many ways there are to pick R of them. So like, let's say we have like 100 books, and we want to take 6 of our books. Okay, so N would be 100, and R would be 6. But okay, so that's with both permutations and combinations. The only difference between permutations and combinations, right, we're still taking a pool of N things and selecting R of them, is whether or not order is important. Okay, so if I switch the order and I have to count a separate event, kind of another tally mark, then we're talking about permutations. And if it doesn't really matter if I switch the order or not, we're talking about combinations. So like when I have my 100 books and I'm going to select 6 of them, do I only care which 6 books I'm choosing? Or am I going to make like a stack of books and I care which one's on the bottom and which one's next and which one's next and which one's on top? Right? If I'm going to make a stack of books, right, and if I switch the order, then it's a different situation. That's permutation. But if I just care about which 6 books I have, I'm talking about combinations. So that's the difference there. And then the last thing I kind of put under this, like, I wanted to conclude it in like the vocabulary definition slide because it's a little bit less intuitive. You just kind of have to take it as a definition. Is that 0 factorial is defined to be 1. If you don't know what a factorial is, we will definitely talk about it at the end. But I just wanted to make sure that this was in the definition slide. And again, we'll talk about what factorials are at the end, but if you already know what factorials are, but you don't know what 0 factorial is. And factorial, the word I'm saying, factorial, that's the what we say for that exclamation point. That exclamation point is read out loud as factorial. So whenever you see 0 factorial, you want that to be 1. And that's just the definition of 0 factorial, which is why I included it here. So that's the vocabulary I have for you. And now I want to go on and do some problems. But I want to pause here and find out if you guys have any questions before we move on. Typing. Okay. So, all right, let's move on. So I'm going to do some problems, right? So I gave you guys that link to the exam guide. So if you look at this, and that's in the, if you go up to the chat box, it's the second one down, the exam study guide. And if you look at it, it basically says like some similar problems and things that you can do for different problems on the homework. So the problems that I'm going to do here also correspond to like the problems on the exam and the problems on the study guide. I'm not going to do all of them. I'm going to do the ones that I think people have either the most trouble with or there's some kind of trick, and some just kind of to give you guys a general review. Okay, so starting with example problem 1. Suppose you roll a die 100 times and a 4 comes up 17 times. What is the probability of rolling a 4? Okay, and so what's important here is that you don't want to assume that this is a fair die. So what is the probability of rolling a 4? This should be pretty straightforward, right? So this is an example of what's called empirical probability, where as opposed to kind of starting with something that every single thing is equally likely, we're figuring out probabilities based on experimental data. Okay, so that's why I kind of wanted to include this, because it's people when you start learning kind of classical probability and you kind of calculate everything, people forget about empirical probability, where you're just kind of using your experimental data to define probabilities, right? So in empirical probability, if you're rolling your die 100 times and the 4 comes up 17 times, then you're going to say, based on this data, I'm going to assume that the probability of rolling a 4 is just 17 out of 100. I'm going to, I don't know why it half became orange, yellow. Okay, so I'm going to use my experimental data to define the probability. Yes, no, a little bit. So I think the reason some people get this wrong is because it's like so simple that people assume that there's more of a trick to it. Okay. No? Okay. Okay. This says answer already, but we're not. All right, so problem 4. So an experiment is conducted, and the resulting sample space is S equals 1 through 12. Okay, so now we're assuming that this is a equally likely sample space, right? We're kind of pulling these numbers out of a hat, right? The probability of getting a 1 is the same as probably getting a 2, right? So that's our sample space, right? All of the possible outcomes. So E is going to be the event 2, 3, 4, 5, 6, and H is going to be the event 1, 2, 3, 4. So the first thing that they want to do is just to list the outcomes in the event E or H, right? So this is a matter of understanding what does it mean, E or H? Well, in order for something to be in E or H, it needs to either be in E or be in H. So anything that's in either E or H gets to be in. So 1 is in, right? 1 is in because that's in H. 2 is in, 3 is in, 4 is in. Those are all in H. 5 is in, right? Because that's in E. 6 is in because that's in E. But 7's not in either. 8's not in either. 9's not in either. 10, 11, 12. Those aren't in either. So anything that's in either E or H is in E or H, right? So this E or H is essentially, it's a new event, right? This should have brackets around it, but, right? Because any subset, right, any collection of outcomes is an event. So instead of just giving it one letter, we're giving it the name E or H, okay? And another way of thinking of it is like, if anything that comes up in E, if anything in E comes up, you win. And if anything comes up in H, you win. So in E or H, you can say, like, I win as long as either E or H is selected. I don't know. Maybe that wasn't a great way of saying it. Okay, so this is what it means to say the event E or H. Okay, so now we want to find P of E or H. Okay, so this is kind of what I was talking about in that tip. Pay attention to what you're being asked. Right here, they're just telling you to list the outcomes. And now they're telling you to find P of E or H. They want you to find a probability. How do they want you to find the probability? They want you to find the probability by counting the number of outcomes in E or H. So they're saying, how many things are in E or H? 1, 2, 3, 4, 5, 6 things in E or H out of a total of 12. So just by that, right, we can use this little formula here that the probability of being in E or H is just the number of things, right, the number of outcomes in E or H divided by, right, so N of S, the number of outcomes in S, the entire sample space. So number of outcomes in E or H divided by the total number of outcomes in the sample space. So there are 6 unique outcomes in E or H. There are a total of 12 unique outcomes in S, right? So this 6 is this top N of E or H. This 12 is the bottom, the denominator, N of S. Okay, so the probability of E or H is 6 out of 12, which reduces to 1 out of 2. Okay, so we did that by counting the number of outcomes in E or H. Okay, now we also have another way of figuring out P of E or H, right? We can do it using what's called the general addition rule. Okay, let me see if I gave it to you here. Right, so just before we even do this problem, the answer to B and the answer to C should come out to be the same, right? But you should definitely still do both parts because it's a good way to check your work. But in both cases, we're finding the same probability. So even though we do it a different way, it should come out to be the same. So let's find this probability using the general addition rule. Here's what the general addition rule is. It says that the P of E or H equals P of E plus P of H minus P of E and H. Okay, so let's break this down a little bit. Let me just see what I did in my slides. Okay, so the first thing I did is I'm just going to kind of show you what these probabilities are, and then I'll kind of explain to you why things are happening the way they're happening. So first of all, P of E is 5 out of 12, right? Because there's 5 things in E out of a total of 12. And P of H is 4 out of 12, right? There's 4 things in H out of a total of 12. And I'm just going to leave the denominator as 12 just to make my addition and subtraction a little bit easier here. So now I need to figure out P of E and H. So just like in order to be in E or H, you need it to be in E or B and H, right? In order to be in E and H, you need to be in both E and H, right? So I got P of E and H is 3 out of 12, right? So what does that mean? E, and maybe I'll type this in the chat because I didn't put it on the slide, right? So E and H, is all of the things that are in E and also in H. So 2's in both, 3's in both, and 4's in both, and that's it, right? So to be in E or H, you need to be in E or in H. And to be in E and H, you need to be in E and also be in H. And there are 3 things that are in both E and H. Okay, so the P of E and H is 3 out of 12. So now we can take these 3 things and we can plug it into that formula for the general addition rule. And I'll walk you through why this works. So plugging in, right, P of E or H equals P of E plus P of H minus P of E and H. 5 out of 12 plus 4 out of 12 minus 3 out of 12. So what's going on here? If I take my 5 out of 12, I'm basically counting 1, 2, 3, 4, 5 out of 12. And then I count this 4 out of 12. So plus 1, 2, 3, 4. And if I were to just kind of add those together and I would get 9 out of 12, I would realize that I made a mistake, that I accidentally overcounted. Right, because the 2, I accidentally counted it twice, because I counted it when I was counting these guys, and I counted it again when I was counting over here, and I was counting these guys. And the 3 and the 4 are the same thing. So 2, 3, and 4 each accidentally got counted twice. So in order to make sure that, they each only get counted once, that's why I'm subtracting off the 3 out of 12, because those got double counted. So now I have my 5 plus 4 out of 12, so it's 9 out of 12, but oops, 3 of them got double counted, minus 3 out of 12. So I'm left with just 6 out of 12, which is 1/2. So you get the same answer both ways. Excuse me 1 second. Yeah, sure, thank you. All right, sound good? All right. I'm going to keep going, and just in general, my rule is going to be I'm going to keep going unless I hear otherwise from you guys. All right. What is the addition rule for disjoint events? Well, remember what disjoint events are. Disjoint events are events that if one happens, the other one can't happen, right? So they can't both happen at the same time. So if you think about that last problem, where we had to kind of subtract off the things that were in both, right? 2, 3, and 4 are in both. If we have disjoint events, there's nothing that's in both, right? You can't have something, like you can't have like 2 be in E and also in H if they're disjoint, because then if 2 happened, then they would both happen at the same time, right? So disjoint events, there's no overlap. So if you happen to have disjoint events, right? So, or mutually exclusive, right? If E and F are mutually exclusive or disjoint, then P of E or F equals P of E plus P of F. And in this case, you don't have to subtract off the overlap. You don't have to subtract off P of E and F because there is no overlap, right? There's nothing there. It would just be doing like minus 0. So let me just see if I went on. Right, so notice that if E and F are mutually exclusive, right, then P of E and F equals 0. So if you don't want to learn another rule, if you don't want to have to like think about this addition rule for disjoint events, it's okay. You can still use this general addition rule because you would just end up like subtracting 0, right? You just end up with like P of E plus P of F. Okay, so fine. So I subtract 0. But because you have mutually exclusive events often enough, and it does simplify your equation, right? Some people find it very helpful to have a separate equation in the case of mutually exclusive events. Okay, So now let's start to get into some of the meat of this. All right. Among Americans who consider themselves auto racing fans, 59% identify NASCAR stock cars as their favorite type of racing. And you know, I've been using these slides for 4 terms now, and I got some of these problems from somewhere else. I don't even know if, and I keep meaning to look up if NASCAR stock cars are like the only kind of NASCAR cars, or if there's other kinds of NASCAR. But I'm going to go ahead and say that NASCAR stock cars equals NASCAR, and I keep meaning to look this up. So, if 2 fans are selected, what is the probability that they will both identify NASCAR stock cars as their favorite type of racing? And if 4 are selected, what is the probability that all 4 will identify NASCAR stock cars as their favorite type of racing? So the first thing I want you to notice is that this is an and problem. Okay, when we have 2 fans being selected, right, what's the probability that they will both? That means fan 1 likes NASCAR the best, and fan 2 likes NASCAR the best. Okay, so in the general addition rule was for OR problems. Okay, so basically, if you're calculating an or if there's an let me say it this way, if there's an or anywhere in your problem, you're going to want to be doing some sort of addition. Okay, so I'll say like or equals addition, right? So either the general addition rule or the addition rule for disjoint events, right? If you're doing something with and, you're going to want to do multiplication. So that's kind of just a general rule of thumb. And that covers kind of modules 5 and 6, whether they're independent or dependent or whatever. It's just a general rule. Or you're going to have some kind of addition, and you're going to have some kind of multiplication. I guess the only exception would be if you are still like using the general addition rule to calculate an and problem, but you still haven't. Let me say this: if you see the word, if you see E or F anywhere in your problem, use the general addition rule, even if that's not the thing that you're having to calculate. Even if they give you like P of E or F, if there's that or in your problem, use addition. Okay. So here we're moving on to and, which is multiplication. All right. So with this type of problem, I like to kind of give shorthand, like a letter to represent kind of each event. So what I like to do for this like problem is I'll call. Oh, sorry, I have to go along with what my slides are saying. These events are independent. So whenever you see something like this in a problem, like 59% of people do X. 14% of America are lefties. Whatever it is, a certain percentage of the population is X. You have to assume they're talking about independent events, meaning if person 1 chooses NASCAR as their favorite, person 2 will also have. Sorry, if person 1 has a 59% of choosing NASCAR as their favorite, person 2 also has a 59% chance of choosing NASCAR as their favorite. Like what person 1 says has no impact on what person 2 says. Each person individually has that same 59%. Okay, so because of that, we're going to use the multiplication rule for independent events, which means that you can just kind of multiply the probabilities. Okay, so if 2 fans are randomly selected, what is the probability they will both identify NASCAR stock cars as their favorite type of racing? So what I like to do is I like to use this N to represent like a single person choosing NASCAR. So what I say, the way my little shorthand here is I would say like P of N equals 0.59. Does that make sense, that shorthand? Like N is like a single person choosing NASCAR. And it says if 2 fans are selected, what is the probability that they will both identify NASCAR as their favorite? So I think of this as the situation NN, right? The first N means the first person chooses NASCAR, and the second N means the second person chooses NASCAR. Does my shorthand make sense to you guys? Because I'm going to keep using it for several problems. So if it doesn't, I want you to tell me so that I can explain it more. Cool. Okay, so that's my shorthand, right? So NN, we're asking about what's the probability of having an NN. So the addition rule, the multiplication rule for independent events says the P of NN is just 0.59 times 0.59. So each of these n's basically contributes a 0.59. And we want n and n, right? So we want to multiply. So each n is going to give us a 0.59. Okay, so that's all I need to do. 0.59 times 0.59. Oops. Scroll back up. Right, which is 0.59 squared, which is 0.381. Okay, so that's all. So I think the shorthand actually really kind of helps you just kind of see what's happening, right? Two fans, n, n. Then when I calculate the probability, each of those is going to give me a 0.59. Okay, so I just get 0.59 squared. Right, so now, if 4 are selected, what is the probability that all 4 will identify NASCAR as their favorite type of racing? So now what they're asking about is n, 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 n. Right, 4 people all liking NASCAR. Right, so the first person likes NASCAR, that's the first n. Second person likes NASCAR, that's the second n. Right, third person likes NASCAR, fourth person likes NASCAR. Okay, so my shorthand for 4 people all liking NASCAR as their favorite is n, 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 n. And we can calculate the probability of n, 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 n the same way. Right, each one of these n's is going to contribute a 0.59. Right, so it's just 0.59 times 0.59 times 0.59 times 0.59, which we write as 0.59 to the 4th power, which comes out to be 0.1212. Do I have a calculator? Yeah, oh, you know what, I wasn't sharing that. Okay, does that make sense? Kind of just and I think it helps you I think that writing it out like this kind of really helps you just see that each of these n's is going to contribute this 0.59. Okay, so that's that. I'm going to do problem 8, but I actually wanted to do problem 9 first. Okay, excellent. So problem 8 and 9, we're both going to be talking about some at least stuff. And the at least stuff, I think, is probably the hardest stuff on this test. So we're going to do 2 different problems with at least. Okay, so about 13% of the population is left-handed. So remember, every time you see that percent of the population, we're talking about independent events, right? Each person individually has a 13% chance of being left-handed. So we have 2 people are randomly selected. What is the probability that both are left-handed? What is the probability that at least one is right-handed? And what is the probability that at least one is left-handed? Okay, so let's start with A. What's the probability that both are left-handed? Oh, again, these events are independent. Okay, so the probability of having a single L, right, if you just choose one person, the probability that they're left-handed is 0.13. So now, your screen went checkered. Is that better? How about now? Okay, sorry, I had a pop-up telling me that I needed to update some software, and I probably go back on screen. Yeah. Actually, just to there was all I was doing was just kind of giving the 3 parts of the problem. So I'll just give them. This is just the first part of the problem, so you didn't really miss anything. I just had a screen that just had this first part. So about 13% of the population is left-handed. So now we have 2 people who are randomly selected. What is the probability that they're both left-handed? Okay, so P of L, right, a single person being left-handed is 0.13. So, by the way, we're going to need this for later. As long as we're saying the probability of being left-handed is 13%, we might as well say, okay, the probability of being right-handed is 87%, right? 1 minus 0.13, right? 13% is left-handed. Everyone else, 87%, is right-handed. And this is called the complement rule, right? The complement rule says that you basically subtract from 1 to get everything else. Okay? Okay, so it can seem complicated when you're kind of reading it, and you're like, why are you subtracting from 1? Subtracting from 1 is basically subtracting from 100%. Okay, so everyone else. Okay, but in this problem, what's the probability that both are left-handed? So what we're looking for is P of LL. The first one is left-handed, and also the second one is left-handed. So that's just going to be 0.13 times 0.13, right? Each of these L's is going to contribute to 0.13. And since we're doing an AND problem, we're multiplying them. Okay, so that's going to be 0.0169. Okay, so now it's going to get a little harder. What is the probability that at least one is right-handed? Well, so let's look at all of our possibilities. We could have LL, then both left-handed, RL, the first one right and the second one left, LR, right, the first one left and the second one right-handed, or RR, they're both right-handed. So what we could do is, let me actually just go back to this slide. What we could do, which will be what I'll call the slow way, okay, is say, all right, well, so I want to call, okay, anyway, we say like, okay, well, at least one right, I'm flipping back and forth between these slides. All right, I'm going to stick with this slide. Every category except for the first one has at least one righty, right? This RL here has at least one righty. This LR has at least one righty. This RR has at least one righty. So every category except for the LL has at least one righty. So the slow way would be to calculate the probability you're in this category, the probability, right, the probability you're in category 2, the probability you're in category 3, the probability you're in category 4, and add them all up. It's doable in this case. If you had more than 2 people, if you had like 4 people or 5 people, it would be not doable. It would take forever. But it's always faster to do the fast way. So to use this fact that at least one person is right-handed, as long as you're not in the case that they're both lefties, then you have to have at least one person right-handed, right? So every single case except for LL has at least one righty in it. So therefore, the probability of having at least one righty is 1 minus P of LL, right? This is the same thing that we were doing when we did the like 1 minus 13% is 87%, like everyone, it's kind of everyone else, right? So the probability of having at least one right-handed person is 1 minus the only situation where we don't have at least one right-handed person, that they're both lefties, right? It's everything else, so we subtract from 1. That's the complement rule. So we already calculated P of LL, so we just need to subtract that from 1, right? So another way of saying this, right, if I go to percentages instead of decimals, in part A, we calculated that the probability that both people are lefties is 1.69%. So therefore, all the rest of the time, the other 98.31% of the time, at least one of the people will be right-handed. Okay, so once you calculated the probability that both people are left-handed, you can easily calculate the probability that at least one is right-handed. So that's the method you really want to take whenever you see the word at least. Okay, you see at least and you automatically want to be thinking like, oh, what's the opposite, right? The opposite of having at least one right-handed is that they're both left-handed. Okay, so now if we do the other one, what's the probability that at least one is left-handed? Right, again, so here are our 4 choices. So at least one, this is a typo, at least one is left-handed, at least one is left-handed, is everything except for the case that they're both righties. So, the probability of at least one left-handed, again, this is a typo, the probability of at least one left-handed is 1 minus the probability that they're both righties, right? Every situation except the fact that they're both righties. Okay, so then this RR, P of RR, right, since the probability of a single R is 0.87, right, this is going to be 0.87 times 0.87, subtract that from 1, and you're going to get 0.2431. Okay, so that's the at least problem. So does that make sense? How do you guys feel about going over 10 o'clock? Going over an hour? I'm trying to decide if I want to skip the next problem. sticking to an hour is not my strong suit. For Module 4, I knew it was going to be longer, so I just scheduled it for longer. Alright, have a good night. Okay, so let's do problem 11. Let's say you're playing a game. The goal of the game is to get a log across a river. Each person on your team gets to try one time. Assume that each person's success is independent of the others, that each person has a 0.15, there's supposed to be a percent, or 0.15, no, there's not supposed to be a percent, sorry, 0.15 probability of failure, meaning a 15% chance of dropping the log, not getting it across the river. So first, would it be unusual, let's say, for you to drop the log? And then, what is the probability that a team with 2 people will manage to get a log across the river? And then, how many people would have to be on the team so that the probability of getting the log across is greater than 0.9999? Okay, so let's start with A. Oh, so first of all, I wanted, right, just like with N and L and R, right, in our previous problems, I want to define some variables. So A is going to be that you individually, like a specific person, gets the log across. So I called it A for across, right? So that's kind of like L, like the probability of a specific person being a lefty. So A is the probability of you one specific person, getting the log across. And D is the probability, no, so this is something that you're going to have to define yourself. Okay, and so this is just like in the last problem when I was like, I decided to call it L, and you can call it whatever you want. I'm just kind of doing it to like help you kind of understand. So D is the probability that you drop the log. Again, I'm trying to get you to understand like my shorthand, how I'm going to go about doing this. But W is the probability that your team wins the game. Okay. So that's kind of the definitions that I'm going to use going forward, just to use a little bit of shorthand. Okay, so would it be unusual for you to drop the log? So what they're asking for is the probability of you, one individual person, dropping the log, right? And it says the probability, right, each person has a 0.15% probability of failure or dropping it, okay? So 0.15, right? It's not unusual, right? This is greater than, 15% is more than 5%, right? This is greater than 0.05. Okay, so it's not that unusual for someone to drop the log. Okay, what is the probability that a team with 2 people will get the log across the river? So now we're in a situation, right, so in order to win, right, you need at least one person to get it across, right? So you need at least one A. So in order to figure this out, we're going to first consider the case that they both drop the log, right? Because whenever you have an at least problem, you want to be looking at the opposite, right? So you need at least one person to get it across. So what happens if it's not the case that at least one person gets it across, right? If neither person gets it across, that means they both drop the log, right? So in order to figure out the probability of winning the game, we have to first consider the probability of losing the game, right? So you lose the game by both people dropping the log, right? Right. So because it's an at least problem, even though it doesn't say the word at least, right, you have to kind of figure out that it's an at least problem just from the context. Okay, so that's why this problem is so tricky. Right, so in order to figure out the probability of winning the game, you need to figure out the probability of losing the game. And you lose the game if both people drop, because you only need at least one person to get it across. So the probability of DD, right, person 1 and person 2 dropping it, is 0.15 times 0.15, which is 0.0225. So therefore, right, if the probability of them both dropping the log is 0.0225, we want to look at the probability of winning the game, right, P of W. So the probability of winning is 1 minus the probability of DD, right? So, and then before I give you the answer, I just give you another way to look at that, just by like, here are the ways that you can win. The first person can get it across, and the second person can get it across. First person across, but the second person drops. First person drops, second person gets it across. Basically, any possibility except for them both dropping it. So either way you kind of want to think of it, you get the probability of a win is 1 minus the probability that they both drop it, or 1 minus the probability that you lose. And you lose by having both people drop it. So what's that going to be? It's going to be, we already calculated this, right? The 0.15 times 0.15 is 0.0225. So we just have to subtract that from 1, and we get 0.9975. And then I just wanted to point out, right, when this 0.0225 that I'm subtracting from 1, really what I'm doing is 1 minus 0.15 squared. Okay. So now, how many people would have to be on the team so that the probability of getting a log across is greater than 0.999? Okay, well, if 2 people were on the team, it wasn't enough, right? If we look at part C, which I think is part B, but right, if we look at what's right up here, 2 people on the team is not enough, right? Because that's only a 0.9775% chance of a win. So let's see what happens if we now have 3 people on the team. So now that we have 3 people on the team, the probability of winning is now 1 minus P of D, right? Because now the only possible way to lose is for all 3 people to drop it, right? Right. So winning is any situation except for 3 people dropping it. So if we calculate that, that would be 1 minus, right? Each D is going to give a 0.15. So 1 minus 0.15 cubed. Okay, so 1 minus this is the typo. This should just be 0.99663. This is what you get after you subtract from 1. I have to fix these. Okay, so 3 people isn't enough, right? That's not more than 0.9999. So let's go up to 4 people. So with 4 people, the probability of getting a win is 1 minus the probability that 4 people drop it, right? Because now, as long as we don't have 4, like, in order to lose, in order to not manage to get this log across, all 4 people need to screw up and drop it, right? So it's 1 minus d. So 1 minus 0.15 to the 4th power. Still not high enough. All right, let's try 5 people. Now, in order to get a win, 5 people have to drop it, right? So now it's 1 minus P of d. So 1 minus 0.015 to the 5th power. And that comes out to be high enough. So what we get is that 5 people are needed to make the probability of the team winning greater than 0.9999. Okay? So this is a tough problem, primarily because it's actually an at least problem, but it doesn't actually have the word at least anywhere in the problem. Right? So you need to be able to kind of just use, your intuition and kind of realize that in order for the team to win, at least one person needs to get it across. So so there's like this hidden at least going on here. So that's what makes this problem kind of tough. Okay. Problem 11. The probability that a randomly selected individual in the U.S. who's 25 years and older has at least a bachelor's degree. Okay, so this has the word at least in it, but it's not actually an at least problem. So we're doing the other side. That has at least a bachelor's degree is 0.279. The probability that an individual in the U.S. 25 years and older has at least a bachelor's degree, given that the individual lives in Washington, D.C., is 0.485. Are these events, bachelor's degree and lives in Washington, D.C., independent? What do you think? The one that we just did was for number 8. Okay, you're saying that yes, these are independent. Anyone else for problem 11? So I'm going to go ahead and say that, let me see what Krista says. We have 2 for independent. All right, I am actually going to go ahead and say that they are not independent. Because remember what independent was. Remember, like we said that like Tuesday and raining were independent. Like one has no impact on the other. Like if I tell you it's a 30% chance of raining, but then I give you this new information, oh, by the way, it's Tuesday. If they're independent, you say, so what? That doesn't change the probability. Here, we have a probability changing. Right? If I just say, like, I pick a person, the probability they have a bachelor's degree is 0.279. But then if I introduce new information, oh, this person lives in Washington, D.C., boom, that probability that the person has a bachelor's degree just shot up to 0.485, right? So you might use your intuition. It might be like, oh, these are independent just based on what I think they are, right? But if they give you numbers in the problem, use the numbers in the problem, okay? Because this problem just as easily could have listed 0.279 and 0.279, and then they would be independent, right? If they were both 0.279, then when I then tell you, by the way, this person lives in Washington, D.C., you'd say, so what? Probability is still 0.279. Didn't impact it. But here, the new information did impact it, so they're not independent. Okay, so that's probably what I just said. Right, no, the event's bachelor's degree and lives in Washington, D.C. are not independent because the probability of having a bachelor's degree, given the information that you live in Washington, D.C., that's what this upright line is, right? This is a given, a conditional probability. So with this new information that you live in Washington, D.C., is 0.485. But the probability of just having a bachelor's degree without any extra information is 0.279. So they're not equal. So that's what this conditional probability, right, this upward, this vertical line, the thing after the vertical line is the extra information that I'm giving you. Okay, so given that the individual lives in Washington, D.C. Okay, problem 12. Suppose that two cards are randomly selected from a standard 52 card deck. What is the probability that the first card is a king and the second card is a king if the sampling is done without replacement? Without replacement means that I take a card out and I see what it is, but I don't put it back in the deck before taking out the second card. And then what is the probability that the first card is a king and the second card is a king if the sampling is done with replacement? Meaning I take out a card, I look at what it is, but then I stick it back in the deck and I shuffle it again, and then I pick a new card. Okay, so that's the difference between with replacement and without replacement. And this is a conditional probability problem because when we're looking at the second card and we're trying to figure out if it's a king, we need to use that information. I'm giving you this new information that the first card was a king or it wasn't a king. So these are not independent events, right? Because if we're talking about without replacement, if the first card is a king, it does change the probability that the second card is a king. Because now there just aren't as many kings left to be had. There only were 4 to start with, and now there's only 3 of them. Right, so the first piece of information does change the second piece of information. So I'm going to do this problem, I'll say 2 different ways. I'm really going to do this problem the same way twice, just using different notation. Just see, because some people, the notation I was using for we'll call it the Module 5 problems, like the LL and the DDDD, some people like to use them here. And some people don't like to use them here because some people think oh, I'm going to assume they're independent. So I'll do it kind of 2 different ways. So here's the first way, not using that notation. So the probability of them both being kings is the probability of the first one being a king times the probability of the second one being a king given the information that the first one is a king. So all of that means, this given that the first one is a king, is that when it comes time for us to consider that probability of the second one being a king, I need to be thinking about what's left in the deck. I assume that the first one was a king, and then say, okay, now what? So the probability of the first one being a king is just there's 52 cards in the deck, 4 of them are kings, so 4 out of 52. Really simple. Now, if we want to now move on to the second card being a king, we need to kind of move our mental mentality, I don't think that's a good phrase, our mentality into a situation that I already pulled a king out of the deck, right? Because I'm looking at the first one being a king and the second one being a king. So if I already pulled a king out of the deck, then what do I have? 51 cards are left because I already took out a card, and 3 of them are kings, right? Because I used to have 4 kings. But now I only have 3. So now, and I think this line is going to go away because I think I added this slide later. Yeah. So now I'm in that location in my head, right, where I'm already assuming that I took out a king. So there's only 3 left. So now the probability of the second being a king, with this new information, right, that first one was a king, is now just 3 kings left out of a total of 51 kings left. Okay? So the probability of them both being a king is I just have to multiply. So 4 out of 52 times 3 out of 51. This one reduces to 1 out of 13. This one reduces to 1 out of 17. So you get 1 out of 221, which is 0.005 or 5%. So another way of thinking of this, so if you wanted to use this other notation, you can still think of this as P of KK, right? The first one is a king and the second one is a king, but you need to still think of like, right, probability of this first king is 4 out of 52. And now when I move on to this second king, right, I'm not just like picking another random person out of the population and like this second person still has a 13% chance of being a lefty, right? This first king is going to contribute a 4 out of 52. This second king, I'm in a new situation, is going to contribute a 3 out of 51. Okay, so if this helps you to still use this notation, go for it. But if it's going to confuse you and make you think that like each k should have the same probability, then don't use this notation. Okay, but it's still kind of, this is the probability of that first king and this is the probability of the second king. Okay, so that's kind of if you like that notation. But don't let that make you think that they're going to contribute the same probability, because they don't. But now, if the sampling is done with replacement, then they actually do end up being independent, but you don't have to use the, they end up being independent in this case, right? The first one being a king has no impact on the second one being a king. But even if you didn't realize they were independent, you can still go ahead and use your conditional probability and it's going to come out to be the same. So the probability of the first one being a king is 4 out of 52. So now what? Now we've been kind of moved into our frame of mind that we've already picked out a king. But what do? We put the king back in and we shuffle it. So for the second card, there are still all 52 choices because I put my card back in and all 4 kings are still in. Right? So this is now the situation that we're in for the second card. So the probability of the second card being a king, even with the information that the first card is a king, right? Even though the first card was a king, or even if the first card wasn't a king, but even knowing that the first card is a king, the probability the second card is a king is still 4 out of 52. So the probability of them both being a king is 1 out of 69, which is 0.006 or 0.6%. And again, here if we want to think of this as P of KK, right, that both K's are going to contribute a 4 out of 52. Because you can think of them as just being independent, or you can still think of it as like, okay, the first king, 4 of them out of 52. Now what? Okay, I put it back in, so now I have 52 cards, 4 of them are kings, 4 out of 52. So whichever way you kind of like to think of it. Whether you think like, oh, now it's independent, I can just go back to Module 5, or if you just want to think of it as like, okay, I'm still going to do this the way I would in Module 6. I'm still going to think about like, what's my new situation? And it just turns out to be that my new situation is equivalent to my old situation. So if that's the way you like to do it. Okay, and then I just have one more problem just on combinations and permutations. It's just a calculation problem. But so if there are any probability questions, this is a good time to ask. I don't see any typing, so I'm going to go ahead. Okay, so one last problem. We want to find 7p3. So what does this mean? So remember when I was talking about combinations and permutations at the beginning, and I said in both cases, right, you're going to have a big pool of n objects, and you're going to take out r of them. So our notation here is that the one that comes first is our n, and the one that comes second is our r. So what this is so 7p3. This, and the P is for permutations. So this is the number of permutations, we say, of 7 objects taken 3 at a time. So meaning if there are 7 people and I want to choose 3 of them to line up first, second, third, right? That would be, right, because there 7 people is like our pot that we're choosing from. How many of them? I'm choosing 3 of them. and I'm choosing them in a way that order matters, right? I'm not just choosing 3 to be in a group. I'm actually choosing a first person, a second person, and a third person. So that's the permutations. So our formula for permutations, and you can see this on page 299, is that it's n factorial. Remember I said this exclamation point is called factorial, divided by n minus r factorial. So on the bottom I have 7 minus 3 factorial. So again, I haven't told you what factorial is if you're not familiar with it, but let me just simplify the 7 minus 3. I hope that's what I did. Yeah, so the 7 minus 3 is 4. So now I have 7 factorial divided by 4 factorial. Okay, so what's this factorial thing? What's this exclamation point? What it means is start to multiply from a number and just kind of go down all the way down to 1. So 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. And 4 factorial is 4 times 3 times 2 times 1. I start at 4 and I go all the way down. And one thing that's nice about factorials is that they divide really nicely. So in this case, right, the 1, 2, 3, and 4 that are in the denominator are all just going to cancel from the 1, 2, 3, and 4 that are in the numerator, leaving only 7 times 6 times 5, which is 210. Okay, so that's how it would calculate this permutation. Okay, and then I think, so here are just some things in the textbook to check out. There's a probability summary on page 284, which kind of summarizes all the rules. There's a summary of permutations and combinations on page 304. And then on in section 5.6, it's kind of taking all these ideas and putting them together. And there's kind of a diagram that kind of helps you figure out which formula to use in which situation. And that's on page 308. So these are just some things in the textbook to check out. Okay, so I actually didn't go so far over, and I even started a couple minutes late, so we were basically perfect. But I'm happy to stick around and answer questions if you guys have any.